And before we start example 4 here, if we read, it says in the figure down here, you can see that this function f of x is 1 over the quantity x squared plus 1. As that approaches, it approaches the same horizontal asymptote to the right and to the left. As we plug in larger x values off toward positive infinity, we see the graph of this function is headed down, and it looks like it's approaching a horizontal asymptote of the x-axis, or y equals 0. And that is also true as we head off to negative infinity, high negative x values. We are looks like we're headed toward the same horizontal asymptote. It says here this is always true of rational functions. But functions that are not rational, however, may approach different horizontal asymptotes to the right and to the left, as we'll see in this next example. And I like to point out here in this function that this numerator is positive 1, so it's always positive. The denominator is quantity squared plus 1. It doesn't matter if we plug in positive or negative x values. We'll square it and add 1, and the result will always be positive. So here we were always on a positive output on the y-axis, and we headed off toward that same horizontal asymptote. And we'll compare that idea to what's going on here in example 4. So when I look at my limit here in part A, it says the limit as x goes to infinity of this function. And if I try right away to plug in infinity, I'll get 3 times infinity minus 2, which is infinity. And in the bottom I have infinity squared times 2 plus 1, which is infinity, and square rooting it really doesn't do anything. So we do have indeterminate form, infinity over infinity. So what we did in a previous example was divided the numerator and denominator terms by the highest power in the denominator. And if we look here at the denominator, it's a little different than what we've encountered before. But if we think about just its essence, when we focus in on that variable, we do have a square root of a quantity squared. And of course the square and the square root are going to cancel, so the square root of x squared is the same thing as x. We are going to divide this through by this quantity. We will divide the numerator by x, and we will divide the denominator by the square root of x squared, which is exactly the same thing. And that way, when we divide the denominator by this square root of x squared, since the square roots are the same, we can have it all under one big radical. So we are going to take the limit as x goes to infinity of, we're dividing our numerator terms by simply x. So let's see, we're going to have a 3x over x minus 2 over x. And our denominator, we're dividing by this square root of x squared, and again that will go under one big radical since they're both square roots. So we'll have our 2x squared term divided by the x squared, and our plus 1 over the x squared. And now we think about letting that x value go to infinity. These x's cancel. So we're going to have 3 minus 2 divided by infinity, which that term is of course 0. 3 minus 0 is 0. Or 3, excuse me. Here in the denominator, our x squareds will cancel, and we'll have this square root of 2 plus 1 divided by infinity is again 0. 2 plus 0 under that radical is just a square root of 2. So there is our limit, the 3 divided by the square root of 2. Now here in part B, this might be a little bit confusing. We are dealing with now x values on the left side of the origin. We're dealing with negative x values. And let's think about this. These two ideas here, x and the negative square root of x squared, are exactly the same. Again, this is just for negative x values. If I plug in a negative x in place of this x, I get negative x. If I plug a negative x in place of here, I will have a negative x quantity squared. So now if I perform this operation, negative x times negative x is positive x. So under the radical I now just have an x squared. And the square root of x squared is just x, so the square and the square root cancel, and I'm left with this negative sign out front. So this will be negative x, and that's equal to this negative x. Again, so this holds true for negative x values. And because I'm heading toward negative infinity, when I do my division, I'm going to divide my numerator by x, this x, and I'm going to divide my denominator by this. I will divide by a negative square root of x squared. If that was a little confusing, hang in there. When this is all done, I show you something the book doesn't. It's more of an intuitive approach to this problem, and it can be whittled down and be a little simpler. So let's see here. We're going to have our limit as x approaches negative infinity, and we got our divisor line. We are dividing the numerator just by a positive x. 3x over x minus 2 over x. And then we are dividing our denominator by this negative second root or square root of x squared. So again, that's all going to go under one big radical. And this negative sign comes along for the ride, so that's out front. And now we're going to have our first term under the radical, 2x squared divided by x squared. And our plus 1 also under the radical divided by x squared. So now we again apply this idea of the limit. So these x's will cancel. And we're going to have minus 2 divided by negative infinity. Any constant divided by infinity, positive or negative, goes to 0. So up top we're going to have 3 minus 0, or just 3. Down under the radical, these squareds cancel. The 1 divided by, again, negative infinity squared, that will 0 out. So we're going to be left with a negative, our square root of 2. 3 over square root of 2, and this is the negative. So when we head to the positive end behavior, to positive infinity, we have a positive horizontal asymptote. As we head toward negative infinity, we do have a negative horizontal asymptote. Different asymptotes to the left and to the right. And let's bring up the graph on this one. So here's the graph of our original function. That 3x minus 2 over the radical. And as we head off toward positive infinity, again, we're headed toward this horizontal asymptote, 3 over root 2. And as we head off toward negative infinity, we dip below the asymptote and we're heading back up toward it, but we are approaching it in the long run toward negative infinity. And again, that is negative 3 over the square root of 2. Oops. And again, I said there was a slightly more intuitive way to look at this problem. If I get this clutter out of the way, our part A and radical, or part A limit was that 3 over root 2, and in part B, negative 3 over root 2. And if we just analyze the function, disregarding the limit for now, if we look at that numerator is just 3x minus 2. It can be positive or negative. For positive x values, we'll have 3 times a positive is positive, and for most values we'll minus 2, and that will usually give us a positive value. The denominator here, we have under the radical x squared. So anything we plug in for x will be squared, it will be positive. Times 2 is still positive, plus 1 is still positive, and then we can square root that. So no matter what, this denominator will be positive. Positive divided by positive tells us for large values of x, for values as we head out toward infinity, we will definitely have a positive limit as we approach it. Down here in part B, now we're plugging in x values headed toward negative infinity. So 3 times a negative will be negative, and minus 2 will be even more negative. So this numerator for negative values will always be negative. And again, the denominators are exactly the same. Quantity squared times 2 plus 1, that is always positive. We square root, and that maintains its positive sign. So here, for large negative values, we'll have a negative numerator, a positive denominator. So we know in the long run, our limit will be negative. And if we think back to the shortcut of just about comparing powers here, earlier I did note that x is exactly the same as the square root of x squared, because the square and square root cancel. X is equal to x. In the long run, as we head way off toward positive and negative infinity, constants drop off. They are inconsequential to the problem. This x squared under the radical is the same thing as x. So this we could break it apart as 3x over. The 2 is trapped under the radical, so we will have a root 2. The square root of x squared will come out as an x, and that's where these will cancel. And we just have our 3 over the root of 2. And the same song and dance down here in part B. You know, the negative 2 and positive 1 in the long run are inconsequential. That denominator will simplify to the square root of 2. That 2 is trapped. The square root of x squared comes out as an x. And again, we have our 3x in the numerator. The x's will cancel, and we have the same 3 over root 2, but we just have to remember intuitively, as we send this off to large negative x values, this has to be a negative output, that negative 3 over the square root of 2. So in a previous section, we saw the squeeze theorem, and we used that to evaluate limits involving trig functions. We could also use that squeeze theorem for limits at infinity. In example 5, limits involving trig functions, let's look at letter A here. It says, what is the limit of sine x as x heads toward infinity? Now remember, the sine wave starts at the origin, and that it heads off to the right, going between 1 and negative 1. So as we're headed toward negative infinity, or as we're headed out here toward positive infinity, is there a number that we are zeroing in on? No, there's not, because you remember this is an oscillating function, up and down, and that word oscillating should ring a bell from chapter 2. Remember when we talked about the existence of limits, there were some reasons that the limit would not exist, and one of those reasons was oscillating behavior. So even as we head off toward infinity for our sine wave, this limit does not exist. And why doesn't it exist? Oscillating behavior. Now in part B here is where that squeeze theorem is going to come into play. The limit as x goes to infinity of the function sine x divided by x. Let's see here, what do we know about sine x? Sine x, the simple sine x function, always has an output between 1 and negative 1. So let's see here. Well, let's divide everything through by x to get, our middle term here, that sine x, to look more like what we're interested in here in part B. So let's divide everything through by x. Okay, now let's apply this idea of the limit as we head x off toward infinity. So we're going to limit this toward infinity. Negative 1 divided by infinity is 0. Positive 1 divided by infinity is 0. And we know for sure that this value, sine x divided by x, if it's stuck in between those zeros by that squeeze theorem, we know that this limit, the limit as x approaches infinity of sine x divided by x, that limit also has to equal 0. And let's check out the graph for that second one there. Here is the function sine x divided by x, and as we start plugging in bigger and bigger x values, it looks like it's call this a dampening function. It's getting tighter and tighter. We're oscillating back and forth, and as we head off toward infinity, it does look like we're homing in on the x-axis or a y value of 0. And again, I like to take a little more intuitive approach when I'm thinking about this problem. If we just look at the numerator, sine x, again, we know that sine x has to have a value between 1 and negative 1. And our denominator is x, and as we think about that as a limit as x goes off to infinity, the numerator is always going to be between 1 and negative 1. The denominator is going to grow off toward infinity. So we have a finite number. Sure, it might not be a constant finite number. It's not always the same number, but it is a number between 1 and negative 1. So a finite numerator divided by an infinite denominator is equal to 0. On example 6 here, a little more real-world application, oxygen levels in a pond. Suppose that f of t measures the level of oxygen in a pond, where f of t equals 1 is the normal unpolluted level at the time t, which is measured in weeks. When t is 0, the organic waste is dumped into the pond. And as this waste material oxidizes, the level of oxygen in the pond is given by this function. F of t is t squared minus t plus 1 divided by t squared plus 1. What percent of the normal level of oxygen exists in the pond after 1 week? After 2 weeks? After 10 weeks? What is the limit as we send t time off toward infinity? So for the first couple questions, they asked us that we're just going to do a simple evaluation. They're asking us to find, this is f of t when t is 1, t is 2, and t is 10. So first we're just going to do a simple plug and chug, f of 1. That's going to be 1 squared minus 1 plus 1 over 1 squared plus 1, which is equal to a half. And they're asking, about oxygen levels. If we want to think percentages, 1/2 is 50%. Next, they asked us to find, after 2 weeks, f of 2. So that's going to be 2 squared minus 2 plus 1 over 2 squared plus 1. And if we compute all that, we get 3/5. 3 divided by 5 is 0.6, and that would be 60%. 60% oxygen level after 2 weeks. Last was 10 weeks, f of 10. And that would be 10 squared minus 10 plus 1 over 10 squared plus 1, or 91 over 101, which is pretty close to 90.1%. So as time goes by, the oxygen level is increasing. What is the max oxygen level? What happens as we send time off toward infinity? Well, we could take this original function and we see that we have t squared in the numerator, t squared in the denominator, divide through by that highest power in the denominator. But remember, we had that little shortcut. The powers of t are the same. We do have coefficients of 1 in front of those variables. So we can disregard everything after them. The t squareds will cancel, and our limit as we approach infinity would be 1, or in percentage terms, 100%. And we do have a graph for this example. Let me pull that up there. Okay, here's our graph, our behavior for the function. As we started off at 0, we have our beginning point here, 1 and 0.05 was our first output the first week, 50%, and then our 0.2, 0.6, and then as we head up, we are leveling it out, but as we head off toward infinity, it does look like we're going to head toward a 100% oxygen level. The level of oxygen in a pond approaches the normal level of 1 as t approaches infinity. Okay, next it's infinite limits at infinity. Many functions do not approach a finite limit as x increases or decreases without bound. For instance, no polynomial function has a limit or a finite limit at infinity. As we head off toward x toward positive infinity, we're not going to zero in on some number like 3 or 5. The following definition is used to describe the behavior of polynomial and other functions at infinity. So let f be a function defined on the interval from a to infinity. The statement, the limit of f of x as x goes to infinity equals infinity, means that for each positive number m, there exists a corresponding number n, also positive, such that f of x is greater than m whenever x is greater than n. Again, this is just, our formal definition. And let's see if we can draw a little graph that goes with this. So let's say on this graph I have some increasing function that's heading way off toward infinity. And what this part 1 of the graph here says, that you can pick some number on the y-axis here. See, maybe about here. You can pick any number and you can say that I want an output of this function that's greater than m. And no matter how high of an m value you pick on the y-axis, I can always come down here to the x-axis and say, well, if you want an m value higher than that, I can give it to you. All you have to do is use an x value greater than this number, greater than n. So again, let's read it again. The statement, the limit of f of x as x goes to infinity equals infinity, means that for each positive number m, again, you're picking some number on the y-axis, for any positive number m on the y-axis, there is a corresponding n value down here on the x value, or x-axis, such that f of x, my output, f of x is going to be greater than the m value that you want whenever you use the x value here bigger than n that I gave you. And this also corresponds to negative infinity, but on the other side, and we're looking for an f of x is less than m whenever x is greater than n. And these definitions can, corresponding definitions can be given for, as we head to negative infinity, we head off to positive infinity, and for x heading off to negative infinity, we also head to negative infinity. Here in example 7, it just says find each limit. These are pretty basic ones. So let's see. So find each limit. Part A, the limit as x approaches infinity of x to the third. And if we think about this graphically, you know, we're plugging in positive x values 1, 2, 3. As we plug in bigger and bigger positive x values, we're cubing them, so the output is much bigger than what we put in, and it's also positive. So as this graph, as we plug in bigger and bigger x values, our y values head off toward infinity. The limit as x goes to infinity of our x to the third function is equal to infinity. We increase without bound. And let's see what happens here on the other side. We're heading off toward negative infinity on the x-axis. So again, we're plugging in negative values of x into a third power function. A negative cubed has a negative output, so we will be working our way down the y-axis. So the limit as x approaches negative infinity of this x to the third power is equal to negative infinity. Again, here's a more precise graph. But again, we're heading up to the right toward positive infinity, down to the left. So as we head off toward that negative infinity on the x-axis, we're headed toward negative infinity. Positive on the x-axis, positive infinity. When we look here in example 8, we see in part A, find the limit. X is approaching infinity of 2x squared minus 4x over x plus 1. If we just concentrate on the greatest powers of x here, we have an x squared in the numerator. We have an x in the denominator, so our numerator is going to overpower that denominator. And I can tell you right off the bat that this limit is going to be toward infinity. And the bottom one here, as our x values head off toward negative infinity, same scenario here, we are just going to head off toward negative infinity. Well, excuse me, we might not be so sure that that's heading off toward negative infinity. Some functions, as we head off toward negative infinity, the function itself might be heading toward positive infinity. So this might take a little more investigation here. And when we look at we need to figure out more about how this function is behaving as it heads off toward, those positive and negative infinity. And we have a rational function here. We have a division scenario setup. So let's fall back on a little algebra 2 long division. So we're going to take our numerator 2x squared minus 4x, and we're going to divide into that the quantity in the denominator x plus 1. And let's see, here we need a 2x squared, so we got to multiply by 2x. 2x times x is 2x squared. 2x times 1 is plus 2x. And we are going to subtract. So we subtract those, and we get nothing. negative 4x minus 2x will be a negative 6x. So next here we have to do a negative 6 times x is negative 6x. Negative 6 times 1 is negative 6. And again we subtract. So we're subtracting, we'll add the opposite and those will cancel. Add here and we will get a remainder of 6. So we've divided in and we have this remainder of 6. So after our division we have 2x minus 6 plus our remainder over our original divisor. So this function, when we divided it out, is 2x minus 6 plus 6 divided by x plus 1. And so again, when we think about heading off toward positive and negative infinity, it doesn't matter which direction we head, positive or negative. This term on the end here, when we're dividing by this quantity x plus 1, no matter if x is positive or negative, that's going to divide into that 6 and just wipe it out. So we can think in the long run, as the limit, or as x heads off to positive or negative infinity, this function is going to behave exactly like our the function will behave just like the function we have here, 2x minus 6. The function will behave like 2x minus 6. And what is 2x minus 6? It's a line. It's a straight line, positive slope. So quick little sketch here, 2x minus 6. And we're not even concerned about the y-intercept being negative 6. We just know it as a positive slope. So as we head off toward positive infinity on the x-axis, our original function will also head off toward positive infinity. And as we head toward negative infinity, again, our function in the long run is going to behave just like this line. As we plug in negative x values, we will head off toward negative infinity. And the graph here is pretty interesting. When we did that division, we divided and found a line. That line was an asymptote. Oops. We did our long division here, and we found 2x minus 6 is how the function would behave in the long run. So again, that's our asymptote. It's not a horizontal asymptote. It's not a vertical asymptote. But it is an asymptote of the function. As we start plugging in these positive values headed toward infinity, our function is going to just get really close to that line, that 2x minus 6 line. And the same thing as we head toward x values of negative infinity. Again, here's our function. It comes up. We have our little max value, and then we start heading off toward negative infinity, just like that line does.